Let's start by looking at a classic paradox from the Greek philosopher Zeno. Okay? Now, Zeno, here he is showing the doors to truth and falsity, veritas et falsitas. And it's in Madrid. Hope you get to see it someday. Okay? No, inappropriate. Lollipops in class? No. No. Not in my class. Okay? I'm going to use the other side. Use the side with ink. Okay? Late. Now, to get across the hall, clearly, Zeno knew he could do it. Right? Let me show you with my magic Zeno slider. See, here he is. Zoom! I can get across the hall. That's great. But, as the Greeks were wont to do, they thought about it a little too long. And they said, well, I have to get halfway there first. This will take a finite amount of time. Let's say half a minute. He's walking kind of slow. Then, it's going to take another finite amount of time to traverse half of what's left. So we add a quarter, another quarter minute, right? And then an eighth, and then a 16th, and a 32nd. He doesn't quite get his nose to the other end of the rectangle there. Because he reasons, I will have to take an infinite sum of finite bits of time, and therefore never reach the wall. But the paradox is, he does.
You drop a book every time it divides in half, so mathematically that hits a 4, but it does.
Well, but how do we resolve this paradox? Because this is an infinite sum of finite bits of time. Now, you've dealt with this paradox a lot. You know how your teachers would mark it wrong when you put down 0.33333333? Because that's what it was on my calculator. I took 1 divided by 3, and I put down everything in the calculator. The calculator's exact, so this must be the exact answer. And now, why is that bumpy?
Because you express something that's not infinitely a finite amount of numbers.
1/3 cannot be expressed as a finite decimal. When you try to change 1/3 into a decimal, you have to write it 0.3 rapidly. It is an infinite decimal. It's an infinite sum of little bits. So we're going to see how we can take this 1/2 plus a 4th plus an 8th and have that sum equal 1. But there's another part of the paradox here too, though, that Zeno, I think, still has a point here. Nobody has countered this yet, that we're trying to write the trick as an infinite sum of finite bits of time. Why isn't that an infinite amount of time then? What's happening to those finite bits of time? They're being cut in half, and they're getting infinitesimally small. So you can't just say it's an infinite collection of finite bits of time, ergo infinity. You have to think of what is happening with those finite bits of time. They're getting smaller and smaller. That's like saying 0.3 replicate is infinite because we can never add it all up. No, it adds up to exactly a 1/3. But if you have to take the infinite sum. Okay. Now, we're going to analyze infinite sums by looking at the sequence of partial sums. So get used to this difference in notation here. Big S is the infinite sum. Okay? Big S is the infinite sum. Now, you could put a subscript infinity there if you want. Not necessary. If the subscript's missing, it means the sum of the entire infinite sequence. S sub n is a partial sum in the sum of the first n terms. So S sub n is t sub 1 plus t sub 2 plus t sub 3 plus t sub 4 plus ... out to t sub n. Where S equals the infinite sum, S sub infinity, which is t sub 1 plus t sub 2 plus t sub 3 ad infinitum without end. Okay? Now, so here's S sub 1, which is always equal to t sub 1. Because it's the sum of the first one term. So those two are always the same. But S sub 2 is the sum of the first two. And what do you get here? 1/2 plus a 4th? 3/4. 2/4 and 1/4, 3/4. And now 1/2 plus a 4th plus an 1/8. 7/8. a half plus a fourth plus an eighth plus a 16th. We can take our old answer of S sub 3 and add on 1/16th rather than redoing all this addition. 15 16ths? 31 32. Can you think of a formula for S sub n?
Equals
Oh,
1
yeah.
minus
It's-
Work on the bottom first. Work on the bottom first.
To the n. To the n.
Two to the end on the bottom, okay?
To the n minus 1.
There you go. There you go. Okay. There's a formula for the n term. Is that the infinite sum then? No, that's stopping at some point in the series and saying I'm just going to add up this many. So it's still not the infinite sum.
So is that a small s or something?
No, that's the big S. That's the big S sub n. Sum of the first n terms. Now, an infinite sum is defined as the limit of the sequence of partial sums S1, S2, S3, S4, S5, Sn, out to infinity. So, there is no one term that is S in this sequence. It's the limit of this sequence. And it is defined as the infinite sum then. S, the infinite sum then, is the limit as n goes to infinity of S sub n. Okay? That's our formal definition for an infinite sum. Okay? So in our last example, we add up a fourth, a half, an eighth, a 16th, 32nd, and we conjecture that the infinite sum is 1 because the sequence of partial sums is getting closer to 1. The limit as n goes to infinity of S, the infinite sum, equals the limit as n goes to infinity of S sub n, which is equal to the limit of this sequence here. That's what it equals 1.
How do you define the limit that's
Well, this one seems to be getting closer and closer to it. Let's actually try it with some of our tricks from yesterday, okay? If we look at it this way, the limit as n goes to infinity of, what did you say the formula was? There you go. 2 to the n minus 1 over 2 to the n. So we can think of that limit as n goes to infinity of 2 to the n over 2 to the n minus 1 over 2 to the n. So it's the limit as n goes to infinity of 1 minus the limit as n goes to infinity of 1 over 2 to the n. Right? Which is 1, right? And this, we can think of this as a half to the n, and our common ratio is between -1 and 1, so it's going to approach 0. There you go. Because we can think of this as 1/2 all raised to the n. And we had a rule for that. R to the n. If r was between -1 and 1, then the sequence is approaching 0. Okay? All right. So, if the sequence of partial sums has a finite limit s, then the infinite series is said to, well, you didn't catch that one, Maddie, is said to what? Converge. Converge.
Oh, one at a time. No, we play like Hangman with this. Diverge.
And then it's diverge. If the sequence of partial sums approaches infinity has no limit, then the infinite series is said to diverge. Diverge.
Let's play Hangman.
Is said to. There's one coming up.
Are we going to play Hangman with this?
With something trickier that somebody just didn't catch from the video ahead of time, okay? Or maybe they looked at the notes ahead of time. Sum of an infinite geometric series then. If the absolute value of r is less than 1, then the infinite geometric series converges. Because what's going on with each of these terms you're adding on? Are they getting bigger or smaller? Smaller if absolute value of r is less than 1. So you're adding on smaller and smaller and smaller bits. So now that in itself doesn't guarantee convergence. But if it's a geometric sequence and you keep adding smaller bits, it will add up to this. And we'll do the proof to be sure. But do you remember this formula? That's it. It's the easiest formula, and it comes out of one of the hardest formulas from the section. T sub 1 over 1 minus r. The first term over 1 minus r. We're going to prove the formula in a bit here. But be careful of this other scenario, though. This is if the absolute value of r is less than 1. What if the absolute value of r is greater than or equal to 1, and you don't start with 0? Then what's the infinite geometric series?
Just hangman.
Diverges, okay? We'll come up with a tricky hangman later, okay? Diverges, okay. Now let's go to the proof. Here's the proof. Want to prove that this is going to work for any geometric, right? And I'm missing some stuff on here. Yeah, and n has got to go to infinity. That's our definition of what an infinite series is. It's the limit of the sequence of partial sums.
S equals t over t.
And now we can put in that formula from before that we had for S sub n. No, you're doing a specific one.
No, t sub 1 over.
Right. No. We're going to prove this eventually, but we're going to start by taking the formula for S sub n. Remember, there's a difference here.
N times t sub 1 plus t sub n over.
Yeah.
Let's see.
S times?
No, n times t sub 1.
No, that's for arithmetic. Geometric.
T sub 1 times 1 minus
R to n over 1 minus r.
Yeah, that's the one. That's for a partial sum. The sum of the first n terms in a geometric. And so now we can split this up and say it's the limit as t goes to infinity of t sub 1 times the limit as n goes to infinity of 1 minus the limit as n goes to the infinity of r to the n all over 1 limit as n goes to infinity of 1 minus the limit as n goes to infinity of r. Basically, you can distribute the limit idea over multiplication, subtraction, division, and addition. But some of these things, notice as n goes to infinity is not going to affect t sub 1 at all, so it just stays as t sub 1. Same thing with a 1, same thing with the r. Same thing with a 1 inside here. What about this? Why? Why does this go to 0? Do the St. Patty's Day analysis here. Exactly. Because the absolute value of r is less than 1. That's why that's such a key condition. That's what gets rid of that term. If you did some of those sum ends in geometric homework, you found there was got to be a pain if you looked at the sum of the first 10 because you had this is what gives you all that fraction.
How do you know r is less than 1?
That's the condition right here.
So if r is greater than 1, then you can't find it.
Can't do it. So that's how we get the whole thing equal to t sub 1 over 1 minus r. Our easiest form. Okay? Alright. Find the sum of the infinite geometric series. They tell you it's geometric, so that helps. Now you can't use the infinite sum form unless you know that r is between negative 1 and 1. What's r in this case? Negative 6 over 9. Negative 2/3. You also get it for 4 over negative 6. Negative 2/3. So r is negative 2/3, and the absolute value of r, is that less than, or is that less than 1? Oh my. It's okay. It's just the funky chalkboard here. Is the absolute value of r less than 1? Is the absolute value of negative 2/3 less than 1? Is 2/3 less than 1? Is 2 less than 3? Okay, yes, we may proceed. Okay?
Why is r, what's r?
R is the common ratio of the geometric sequence. That's what you keep multiplying by.
D is for the
Count the difference, that's in there. Okay? So we can go ahead and use the formula. T sub 1 is 9, that's the first term. The common ratio, we just figured that out, is negative 2/3. So it's 9 all over 1 plus 2/3. Let's multiply top and bottom by the overall LCD of 3 to get 27 over 3 plus 2. 27/5.
That's the lowest you can get. Wait, that's a sum. Oh, never
That's the infinite sum. Now you might say, no, wait. 27/5 is, can I say 5.4?
Yes.
5.4? Well, 9 is way over that, but minus 6, now we're down to 3. Now you add 4, you're up to 7. Now you subtract. And it's going to be one of these things where you're going to bounce back and forth and go a little over the infinite sum, then a little below, then a little over, then a little below. And eventually it does converge on this.
So if we found that R wasn't less than 1, we just stop the problem because it'd be infinite
Yeah,
sum?
you can't use the infinite sum formula.
Okay.
Now let's check this with the T99. Yeah, before we get to example 2, let's check with the T99. First, let's just do the sum of the first 10, because I don't know if we can do an infinite sum. Let's try the sum of the first 10.
I just saw that here.
You go to the sigma key. Remember we did this the other day with F3 under calc, because that's what y'all are. Pre-calc H, right? So you're taking the AP courses next year, right? How many of you signed up for AP Stat? Okay. Just so you know, our next chapter, the combined 15/16, is to get you ready for AP Stat. Not that the rest of you won't use it somewhere else, you will. And then the chapter after that, I combined 17 and 18, that's to get you ready for AP Calc. That's going to talk about limits and derivative. So that's pretty much what you're doing in April, pre-stats, and in May, pre-calc. The real pre-calc. So you better know that calc menu. One key thing is the summation symbol, right? Now we have to put a formula in, right? You need a formula for the nth term of the sequence.
So would it be 9 times -2 over 3 to the power of
Right, 9 times, yeah, make sure you put the negative 2/3 all in parentheses, raised to the, can we say x minus 1 for now, just because it's easier, right? Easier to find. And have x go from 1 to 10. And what does it say? Probably not 5.4.
5.306.
5.306. Okay, so not quite, right?
Why isn't it 5.06? Oh, got it.
Because we just did s sub 10. Well, let's try s sub 100. You can just change this to 100 then, right?
But Michelle,
Just do the same thing, scrolling up. I've got a calculator here. You don't have to curse the darkness.
but that's not the.
Share,
It's not
you share.
That's not the formula we got though, Michelle. We
Let's see again.
We did.
That's the
What? Just put an extra 0 in there.
I know. I'm sorry.
Got it.
Is it still rolling or is it still thinking hard? Or 5.4.
That's it.
No, y'all need to float 12, please.
Yes, no, it's 5.4.
And then,
That's fine.
It's just 5.4.
okay, well actually that's kind of handy because it's giving you all those O's because it's probably floating a little something beyond there.
There's a 1.
I got
Yeah, if
it.
you subtract 5.4, it'll probably show you where that 1 is.
Mine has a 1, like.
Yeah, it's like.
But you know, S equals the limit as n goes to infinity of S sub n. We can do this on the calculator, right? Because also underneath your calc menu, what else is there? Limit. Let's try it. Limit on your calculator now of, now S sub n, you've got all this stuff that you can cut and paste in there, right? So summation of 9 times negative 2/3 raised to the x minus 1, x going from 1 to n. See, this is why it gets very picky about specifying your variable. So I can use another variable now to represent how many terms I'm taking. And then all of this is the calculated way we did S sub n, right? But we want to look at the limit of S sub n as n goes to infinity. Well, and I didn't finish, did I? Now I'm done, okay? There.
So should we use x or n?
Now you're doing the limit of the sequence of partial sums.
Does that say to the after the two?
No, comma n, comma infinity.
So there's 2 comma n.
No. Well, yes, because this is saying 1 comma n to finish up our sum idea, right?
But you have to put it in.
And these parentheses go together.
Wait, why did you
And then these parentheses go together. Let me color code them.
Why did you
That green parentheses going with this green one here.
Don't we want to use X though?
Do you have to use
This red parentheses is going with this red parentheses here.
Well, yeah, but don't you want to change it?
This is a raised to, this is a caret.
This is why
Why do I have this n? I have this n here because I want a formula that has n as its variable. Because I want to look at this limit as n goes to infinity of S sub n.
Did anyone get an answer? No.
Which should work.
It's not working.
It should say 5.4. You're probably missing some.
The n will not work. Oh,
Yes, it will.
27
27 fifths, 5.4.
I did.
Yes, Julie?
It's not really.
Shh, can't hear the questions in the back of the room there. Pipe down, Miss Worthies.
Oh, 27.
Still can't hear. Quiet, please. The question might be your question, and then it gets answered. Yes. Yes, this is the definition of infinite sum. Now, there's an easier way to do it in your calculator, though. You can actually think of it as S sub infinity. So here's another way to do S as S sub infinity. Do what we did before. Use the sum symbol. 9 times negative 2/3 raised to the x minus 1. X going from 1 to infinity. Yeah, we can put the infinity there as an argument. Does it like it?
Didn't like it at first, no.
See, so you're basically, by doing it this way, you're stating the step. Instead of saying, it's saying, add up all the terms from 1 up to the infinitieth term. As opposed to, look at the limit of the sequence of partial sums.
So we can say that now instead of that.
Yes, I'll accept that. I offer this because sometimes I've seen the calculator not quite get into this. It doesn't like infinity all the time. Especially if it's a sequence it doesn't recognize or something like that. It doesn't know the formula tricks to do it. All right. Now, for what values of x does the following infinite series converge? Is it geometric? Yes. What's the common ratio? X minus 2. You start with 1 and you multiply by x minus 2 to get x minus 2. So for it to converge means the common ratio, absolute value of that must be less than 1. So that's how you get your series in x. So absolute value of x minus 2 is less than 1. So yeah, put negative 1, x minus 2 in between negative 1 and 1. So you get 1 is less than x is less than 3. That's called your interval of convergence. Now you're going to benefit from kids in the other class starting the homework already, because there's actually a follow-up question on this. What is S for this series? T sub 1 is 1. What's R? X minus 2. Put in parentheses though, so you get 1 over 1 minus x plus 2. Oh, a little psychic there, Mr. Okay. 1 over 3 minus x, right? So now that for it to converge, x has to go between 1 and 3. What are the possible values for the infinite sum then?
1/2 or
If you put in 1, you get a half, but if you put in 3,
It has to be less than 3.
yeah. And you can't apparently get a half, because if you put in 1, it's 1 plus negative 1 plus 1 plus negative 1. How is that a half? The partial sums are what? The sequence of partial sums. 1, 0, 1, 0, 1, 0. What's the limit of that sequence? Is it a half? Is that kind of like a compromise? No, it's divergent. You don't have a limit. So, got to be careful because we can't actually use 1 or 3. Okay? Okay, example 3, the infinite repeating decimal, 4.5 can be written as an infinite series. 0.45 plus 0.0045 plus 0.00045 plus 0.0000045 and so forth. Is it geometric? What's the first term then?
0.45.
And the common ratio?
0.01.
0.01. So the infinite sum, t sub 1 over 1 minus r, 0.45 over 1 minus 0.01, 0.45 over 0.99, 45/99ths, 5/11ths. You can check that on your calculator. 5/11ths hit diamond. So, okay.
So the infinite sum will add up to 5/11ths? Like, what's the
0.5 repetent is 5/11ths. So 0.4 repeating like this, repetent, equals 5/11ths. Just like 0.9 repetent equals
1.
Are you sure? Are you sure?
It's 1.
I'm sure.
0.9 repetent?
1.
That?
It's 1.
It is
0.9 repetent? Are you sure? What was 0.3 repetent? 0.6 repetent? So 0.9 repetent? Who took it out, right? Now you all believe.
Was that right?
Some of you are kind of going, oh, it's missing something. No, it's missing nothing. Just like 0.3 repetent is not missing anything, it is a third. Okay, 0.9 repetent is missing nothing, it is 1. Don't leave something as 0.9 repetent. Now, do you remember the other way? 0.5 repetent, the MS way. I think you learned this in the middle school.
Blanche, that's not 1. That can't be 1. If you put 1 into your calculator, it doesn't come out 0.9.
Yeah, it does.
And if you put 1 into your calculator, you don't get 3/3 either, do you? Just take what you're like thinking of it. In general, the calculator will give you the simplified form. It's not going to come out and give you all the variance on it.
Boom.
That's just because it's rounded.
So much to read.
No, it's not.
Being the system.
What was wrong with my proof, man? Would you like the infinite sum proof? Like, what's the first term in this sequence? 0.9, right? Common ratio? 0.1. 0.9 over 1 minus 0.1. 0.9 over 0.9 is 1.
That's 1.
But 0.99 doesn't equal 1.
It does, because, right. I'll agree. 0.99 does not equal 1. 0.99 equals 99 hundredths. 0.999 is 999 thousandths. None of those are equal to 1. Those are all partial sums. The infinite sum is the limit of that sequence of partial sums, and that will be 1. The infinite sum is 1, right?
Just accept it.
Mark, what do you think's missing now? What was wrong with my proof up here? You told me the 2/3 is 0.6, right? Okay? Let's try this way. Remember this approach? Let n equal 0.45 repetent. So 100n is what?
100 times 0.45 repetent.
45.45 repetent. Subtract 100n minus n is 99n's. 45.45 repetent minus 0.45 repetent is 45. And this is often how students come up with repeating decimals right away. They just take the repeating part and divide it by that many nines. It's a nice little shorthand way to do it. Gotta be careful. It doesn't always work though if you don't repeat all the digits. Like if it's 0.45 right. And again, you get 5 letters. Okay, I believe that's it. Oh, no, we got one more example here. Remember Zeno? Coming along? Zeno, coming along here? Zeno? I gotta grab him from here. Remember Zeno tooling along, getting halfway there, and then half of what's left, and half of what's left again, and half of what's left, and so forth, and so forth, and so forth. And Zeno created this infinite sum, right? A half plus a fourth plus an eighth plus dot, dot, dot. Let's use our infinite sum formula on this now. What's t sub 1? What's the common ratio? Half. A half over a half is 1. Okay. Now, Zeno's friend, Charlie Brown, another great philosopher. Okay? I need a helper here because I'm going to carefully move Charlie Brown halfway, and then someone's going to mark it, okay? Just mark it? Yeah, come on. Here we go. Now, help us out here because this is the Charlie Brown wishy-washy way to come up with 2/3. So someone walked out from respects. This happened to be in Lord of the Flies, too. Okay, there you go. All right. Piggy. His name's not Piggy. Now, class, does that look like a half?
A little to the left. A little to the left.
Good?
That's good. Okay.
Okay, good. We're very good at judging half.
Can I mark it?
Yes, mark it. Mark it. Get right underneath his pointy feet. I actually had to put Charlie Brown's shoes into the pencil sharpener. Now, he gets halfway to the Halloween party and he goes, oh my gosh, it's a Halloween party. I'm not in costume. I'm going home. So now Charlie Brown starts going back. And halfway back of what he had already gone, is that about halfway, half of that again?
There.
Good?
A little to the right.
Little to the...
To the right.
I didn't move it. Okay, fine. Okay, you can mark that. And he goes, I have the most fantastic costume. Look at this, stripes. Right? So he starts going happily off to the party again.
But then he remembers.
But then, is that about half of what's that gap there? No. He gets there, and then he goes, wait a second, this is a Charlie Brown costume. I'm Charlie Brown. Doesn't work. I'm going home. It's going home. And then he goes, wait a second.
There we go.
Mark that. I could get a false ID. That says Axl Rose. Okay? And then I could go to the party as Charlie Brown, and people would, but no, I'm really Axl Rose. Then he goes like this, and then he has a moral dilemma. That would be dishonest. It's not worth it, people. Don't get a fake ID. If you have to go somewhere that requires you to be someone other than yourself, you shouldn't go there. Okay? So he starts backing up and going, I guess I'll just hang. Oh, that's right, it's laundry night. I can't stay home. Okay, mark it again.
Wait, but you're not gonna be able to say that afterwards.
Oh, wait, I didn't really. Okay, let's just make a really thick one right about there.
I'll do it.
So eventually Charlie Brown kind of keeps up doing this wishy-washy thing, and he ends up about where? Yes, make it come down further. That's not 2/3 of the way.
It's 2.
Look at it.
That was...
Would a ruler help? You didn't know he's only traveling 3 inches apart. Okay? It's not going that far. Right? Yeah, that's pretty close. I don't know why I messed up so much in the other class. Okay. So let's see how this works. Now you have a way of estimating the third. Because a lot of times, sometimes, you got pizzas. Don't figure out how to cut it in thirds. It's very difficult. So here we go. Because he went halfway, but then backed up a fourth, and then went forward an eighth, and then backed up a 16th, etc. So it is geometric, First term is a half. Common ratio, though, is negative a half. And that makes all the difference in our formula then. Because then you get a half over 1 minus negative a half. A half over 3 halves. And that's it. And then you can get 2/3 by kind of eyeballing and cutting that in half. Okay. All right. Great. All right, I'll post up the big thing again. What is that? Oh, the tote board.